Okay, now we are going to start our class at this new chapter. So in previous chapter, we have finished a very important concept that is called maximum likelihood estimator. So that has been finished and we continue to chapter 8. So in this chapter, we are going to talk about this square approach. So for this square, as you can imagine, we are going to calculate the difference between the data and also the parameter, the and then calculate square, the square error, and we want to choose the value of the estimation to minimize the square error. So let's take a close look at the concept of this chapter. In previous chapter, we have attempted to find an optimum or nearly optimum. Nearly optimum. That is the likelihood approach, right? By considering the unbiased estimator and determine the one that is exhibiting the minimum variance, that is called the NTHU estimator. We now depart from this philosophy to investigate a class of estimators that, in general, you want to pay attention to this, in general has no optimality property. So, if you would recall previous chapter, we are not even previous in many chapters. We always talk about something to be optimized, likelihood to be optimized. If you optimize the likelihood so as to choose the estimation value, then that will be the maximum likelihood estimator. But in this case, this square approach, in general, it has no optimality property with it, but it makes good sense for practical problems. This is the least square, and it dates back to the old times when people start to study cosmology and planetary motions. A salient feature of the method is that no probabilistic assumptions are made, right? No probabilistic assumptions are made. Uh, that will make the problem at the first sight looks complicated. If you don't have probabilistic assumptions about the data or the noise, then it looks complicated, right? At the first sight. But if we think about it, in many practical applications, we don't have any probabilistic idea about the noise or the data. In such cases, this could be a good thing. It turns out to be a good thing in practice. Okay, so only a signal model is assumed. The advantage then is its broader range of possible applications. On the negative side, on the negative side, no claims about optimality can be made. So we will not be able to say, uh, is this square this square estimation optimal? Of course, it may not be, and most likely it will not be. And also, uh, will it be unbiased? You know, the biasness is one thing we care about. Is it unbiased? We don't have answer for that. Okay, it cannot be claimed to be optimal in terms of the variance. It cannot be claimed to be unbiased. So not even unbiased. So that optimality claim is is broken in this sense. And also the statistical performance cannot be assessed without more specific assumptions about the probabilistic structure of the data. However, the least square estimator is widely used in practice due to its ease of implementation. So it's easy and simple. Okay, so let's take a look at uh, this next page 220, chapter 8.3, the least square approach. Our focus in determining a good estimator has been to find the one that was unbiased and had minimum variance. If choosing the variance as our measure of goodness, we implicitly sought to minimize the discrepancy between our estimate and the true parameter value. So in this square approach, we attempt to minimize the square difference between the given data and the assumed signal or noiseless data. Okay, so we try to minimize the square difference. But will that statement uh, identical to we're achieving CRB? Of course not. Of course not. Okay, it's not achieving CRB. Okay, it's just trying to, in a heuristic sense, it's trying to minimize the square difference between the data and the parameter. Okay, so the signal is generated by some model, which in turn depends upon our known parameter theta. The signal Sn is purely deterministic. Due to observation noise or model inaccuracies, we observe a perturbation of Sn, right? What do we mean by perturbation? Perturbation means Sn plus a noise. We sometimes we call it noise, but sometimes we call it perturbation. So we observe a perturbation of Sn, which we denote by Xn, and the least square estimate of theta chooses the value that makes Sn closest to the observed data Xn. Closeness is measured by our X arrow criteria. Then what is our X arrow? We do it this way. Okay, we do it this way. We name a J theta equal to summation of Xn minus Sn. So where the observation interval is assumed to be n equal to 0, 1 all the way to n minus 1, and the dependence of J on theta is via Sn. The value of theta that minimizes J theta is the LSE. This is called least square error estimator. Note that no probabilistic assumption has been made about the data. So if we take, uh, take a step back and take an overview, when we go from here all the way down to here, you notice one particular very unique feature of this estimator. Have we talked about the data model? This is the first time we try to write out an estimator without even writing the signal model. So now you know this is the thing about this estimator. If we take one step back, it has no probabilistic assumptions, but it loses the optimality. Okay, it has its upside and downside, pros and cons. Okay, so uh, no probabilistic assumptions have been made. You may be curious about this, but as I said, we have to think about this estimator in the sense of this is coming from heuristic, empirical experiences. Okay, it's not a very uh, mathematically rigorous estimator。就是说，这个 estimator 它本身是一个从经验法则，从把这个错误的平方最小化的观念而来的，它并不是一个有很严谨几率基础的一个 estimator。那它的好处就是它很实用，计算起来很简单，但是它没有最佳化的一些特性在里面，并不是说它一定不最佳化，而是它可能很可能没有办法达到 CRB，它很可能达不到 CRB。哦，这个是我们可以这样去理解它。哦，那很多实物上的问题其实也有在用的，不过就是 case by case 哈。像通讯里面 demodulator 也有用 LSE 的这个方法在做 demodulator，但是它效果蛮不好的，它跟 maximum likelihood 差了好几 dB，所以说当我们的 error rate 要降到10的-3、-5的时候，你用 LSE，它的 SNR 是要非常高的。这时候，我们通常还是会想要用比较好的 estimator。但是如果有些东西是对于精确度的要求没那么高，那也许可以用。观念上大概解释一下。Okay, so let's take a look at this first example, DC label signal. I think we have that before, so I'm not going to write down the signal model again. Okay, the signal model is actually Sn equal to A, right? It's equal to A. So if I write it out, it will be X equal to A plus W, right? And this is the noise. So as I said, this is simple and easy. We don't even have to talk about the probability density function. So we will just write out X minus A, because X minus A is equal to W. So we are trying to minimize the square of the error. So we can estimate A by minimizing this X, okay, this X minus A, which is equal to W, and you want to sum it up and minimize it, and then the rest is mathematics calculus. So if you can do it by calculus, the way is that we differentiate it with respect to A and set the result to 0. Okay, we differentiate this and set it to A. No, excuse me, set it to 0，就是把它的一阶微分设成0，这个是我们在解最佳值、最大值、最小值的一个常用的方法。So now you get A, you differentiate this and you get 2x minus A equal to 0. Right? Of course, there will be summation. And then you sum it up. You solve for the unknown A, and then you get this A equal to 1 divided by n summation xn equal to x bar. And this is a sample mean estimator. So you get this LS estimator. You get this LS estimator. And this is our familiar estimator. However, we cannot be claimed to be optimal in the minimum variance unbiased but only in that it minimizes the LX error. We know, however, from our previous discussions that if xn is equal to a plus w, where w is zero mean, and I want to go back a bit. You see, have we talked about the probability of this noise? No, right? No, that's what I want to emphasize. Up, even if we are getting the outcome of the estimator, we have not talked about the noise, the statistics of the noise. So that's the good thing about it. Also, the bad thing about it, because it cannot be optimal. Cannot be optimal. Okay, so but we recall what we did before from our previous discussion. If this is zero mean WGN, we did this many times. If W0 is zero mean WGN, then the RSE will be the MVU. Okay, but we don't do it here, but we did recall what we did in previous chapter. Okay, so if this is zero mean WGN, then this happens to be what? To be MVU, which also achieves CRB. Okay, so but this is coincidence. This is a coincidence. Okay. To emphasize the potential difficulty, consider what would happen if the noise were not zero mean. Then the sample mean estimator would actually be an estimator of this, right? It will, if this is not zero mean, it will be an estimator of A plus this. Since this could be written in this way. So what are you actually estimating is A plus the mean of the noise. As a result, you are going to have a error, right? You are going to have a bias that is caused by this. Then the data are more appropriately described by this. It should be clear that in using this approach, it must be assumed that the observed data are composed of deterministic and zero mean noise. Okay, but if we don't know about the statistics of the noise, how can we claim the noise to be zero mean? In practice, this is not very practical. Usually, we just use it and we assume it, and then if there's an error in the mean of the noise, we just live with it. Okay, we just live with it. There's nothing we can do better than that. Unless you know something and you subtract it out. Like if you know the mean of the noise, you subtract it out. That is a possibility. But if not, then we just live with that. Can we take it? Without actually not much we can do about it. Okay, if this is the case, the error will tend to be zero on average for the correct choice of signal parameter. Okay, the minimization is then a reasonable approach. Okay, and we also want to consider what will happen if the assumed DC level signal model were incorrect. For instance, if it's like this, it varies with time. It has a Bn term that varies with time. Then that thing will be even more biased. So what we are saying is we want to be more cautious about this, careful about this, but in practice it's useful, it's easy and simple to implement. Okay, so it has its pros and also cons. Okay, then we stop for the moment and we will continue next session.